Based on process flow RDBMS schema designed for manufacturing industry with AI/ML. To design an RDBMS schema for the semiconductor industry process flow shown in the image, we can translate the various nodes and flows into tables and relationships. Here's a suggested schema based on the elements in the process flow. 1. Entities table. This table will represent each of the numbered nodes, example 2.0 for bank, 4.0 for others, etc. Entity ID, integer, primary key, unique ID for each entity, example 1, 2, 3, etc. Entity name, string descriptive name for the entity, example bank, government, process X. Description, string additional description or details about the entity. Flow value, decimal numeric value shown within each node, example 17.0, 6.0. 2. Flows table. This table will store the connections between the entities, representing the process flow. Flow ID, integer, primary key, unique identifier for each flow. Source entity ID, integer, foreign key to entities. Entity ID, the starting entity of the flow. Target entity ID, integer, foreign key to entities. Entity ID, the target or destination entity of the flow. Flow type, enum, example information, feedback, material, type of flow, as indicated by different arrow types. Flow value, decimal flow values associated with each connection, example 5.0 and 6.0. Direction, enum, example bidirectional, unidirectional, indicates if the flow is bidirectional, feedback and information flow, or unidirectional, material flow. 3. Flow types table. This table defines the possible types of flows for easier reference. Flow type ID, integer, primary key. Flow type name, string, example information flow, feedback of information, material flow. Flow color, string color code associated with each flow type, for visualization. 4. Entity relationships table, for hierarchical relationships or dependencies. This table can capture specific dependencies or hierarchies between entities, if needed. Relationship ID, integer, primary key. Parent entity ID, integer, foreign key to entities. Entity ID, the parent entity in the hierarchy. Child entity ID, integer, foreign key to entities. Entity ID, the child entity or dependent. Relation type, string type of relationship, example supplies, reports to. Example of data population. Entities table. 1. Bank, financial institution, 2.0. 2. Government, regulatory body, 1.0. 3. Process X, manufacturing process, 4.0. Flows table. 1, 3, 5, information, 5.0 and 6.0, bidirectional. 2, 4, 7, material, 7.0 and 8.0, unidirectional. This schema provides a relational model for tracking the entities and their interactions as per the process flow diagram. Additional normalization or adjustments may be made depending on specific data requirements and relationships. An RDBMS schema combined with AI/ML capabilities at various management levels top, middle, and operational can significantly enhance decision support systems, DSS. Here's a breakdown of how each management level can leverage RDBMS and AI/ML in DSS. 1. Top management, strategic level. Focus, long-term strategy, growth, and risk management. Role of RDBMS. RDBMS provides structured and historical data, which is crucial for trend analysis, forecasting, and high-level strategic decisions. Data can be easily aggregated and summarized across different departments for a holistic view. Role of AI/ML. AI/ML models help identify patterns and trends, enabling predictive insights. For example, in a semiconductor industry, AI could predict demand or market shifts, helping executives make informed strategic decisions. DSS impact. Predictive analytics. AI/ML can forecast future industry trends, risks, and customer needs. What-if scenarios. AI can simulate different scenarios, example market changes, raw material price fluctuations, and assess their impact. Real-time dashboards, RDBMS-backed dashboards with AI insights provide a comprehensive, up-to-date view for quick decision-making. 2. Middle management, tactical level. Focus, resource allocation, project management, and departmental objectives. Role of RDBMS. RDBMS schemas enable middle managers to access detailed data related to operations, costs, resource utilization, and project progress. It allows for tracking KPIs and performance metrics. Role of AI/ML. AI/ML can analyze resource efficiency, quality control metrics, and customer feedback to optimize operations. For instance, machine learning models could detect inefficiencies or quality issues in the production process early on. DSS impact. Optimization. AI/ML can suggest optimal resource allocations and schedules to maximize efficiency. Trend analysis. Middle managers can track trends in quality control, customer satisfaction, and operational costs. Anomaly detection. AI/ML can automatically identify outliers in performance data, helping managers address issues before they escalate. 3. Operational level, operational/transactional level. Focus, day-to-day operations, process optimization, and real-time issue resolution. Role of RDBMS. RDBMS manages real-time data storage, transaction processing, and data logging, providing the data needed for daily decisions. Role of AI/ML. AI/ML models can automate routine decision-making, optimize workflows, and ensure quality control. For instance, AI can monitor and adjust machine parameters in real time to ensure consistency in semiconductor production. DSS impact. Real-time monitoring. AI/ML models can analyze sensor data and operational metrics in real time, alerting operators to any immediate issues. Automation. AI-powered automation, example predictive maintenance, can reduce downtime and increase productivity. Quality control. Machine learning can inspect product quality during manufacturing, identifying defects before they progress through the line. Benefits of integrating RDBMS and AI/ML in DSS across all levels. Improved data quality. An RDBMS ensures data consistency, accuracy, and reliability, providing a strong foundation for AI/ML models. Data-driven decision-making. AI/ML enables data analysis that goes beyond human capabilities, delivering actionable insights. Enhanced communication. RDBMS schemas help streamline data access across departments, enabling all levels to access relevant information. Scalability and flexibility. The structured approach in RDBMS makes it easy to scale and adapt as new data sources or AI models are added. Example application in semiconductor industry DSS. In a semiconductor industry DSS, an RDBMS schema could store process flows, costs, quality control data, and market trends. AI/ML could predict product demand, optimize supply chain logistics, and detect anomalies in manufacturing. Here's how it could work. Top management uses AI insights from the RDBMS to make strategic decisions about new product lines, market expansion, or investment in R&D. Middle management utilizes AI models to optimize production schedules, manage costs, and ensure that departments are meeting their KPIs. The operational level relies on AI to monitor production quality and automate adjustments to manufacturing parameters, improving output quality and efficiency. In summary, integrating RDBMS and AI/ML at each level of management in DSS supports a comprehensive, data-driven approach to decision-making, enhancing efficiency, accuracy, and responsiveness across the organization. In the process of providing AI/ML reports and graphs for top management, the focus is on delivering high-level insights that support strategic decision-making. These reports and visualizations should simplify complex data, highlight key trends, and make it easier for executives to make informed decisions. Here are some essential AI/ML reports and graphs that would be beneficial for top management in a semiconductor industry setting. 1. Market demand forecasting. Description: predictive models can be used to forecast future demand for semiconductor products based on historical sales data, market trends, and macroeconomic indicators. Graph, a line chart or area chart showing projected demand over the next few quarters or years, overlaid with actual sales for comparison. Insights, highlights expected growth or decline in demand, helping executives plan production volumes, inventory, and resource allocation accordingly. 2. Revenue and profit forecasting. Description: revenue and profit forecasts can be generated based on sales data, cost factors, and anticipated market trends. Graph, a bar chart or line chart showing forecasted versus actual revenue and profits for the upcoming quarters or years. Insights, provides a financial outlook and helps top management set realistic revenue and profit targets. 3. Customer segmentation analysis. Description: machine learning algorithms can segment customers based on purchasing behavior, product usage, and preferences. Graph, a scatter plot or clustered bar chart illustrating different customer segments. Insights, helps management understand customer profiles, enabling targeted marketing strategies and better product alignment. 4. Supply chain optimization and cost analysis. Description: AI can optimize the supply chain by analyzing supplier performance, lead times, costs, and demand variability. Graph, a network graph showing optimized supply chain routes and cost breakdown, or a bar chart comparing actual versus optimized costs. Insights, identifies cost-saving opportunities and efficient supply chain configurations, which can significantly impact profitability. 5. Production efficiency and yield analysis. Description: AI models can analyze manufacturing efficiency, defect rates, and yield trends. Graph, a time series plot or bar chart showing yield percentage and defect rate over time. Insights, provides an overview of production quality and efficiency trends, helping top management identify areas for improvement or investment in quality control. 6. Product quality forecast and anomaly detection. Description: machine learning models can predict potential quality issues based on historical production data and detect anomalies in real time. Graph, anomaly detection line graph highlighting periods of high defect rates or quality issues. Insights, enables proactive quality management and helps management ensure that products meet required standards. 7. Competitive benchmarking and market position. Description: AI models can compare the company's performance with competitors, considering factors like market share, revenue growth, and innovation. Graph, a radar chart or benchmarking bar chart comparing the company's metrics with those of competitors. Insights, gives top management insights into how the company is positioned in the industry and identifies areas where the company may lag or lead. 8. Risk analysis and mitigation strategies. Description: AI can assess risks across different areas like supply chain, market demand, and regulatory changes. Graph, a heat map showing risk levels across different factors or a risk impact/probability matrix. Insights, helps executives understand the most pressing risks and prioritize risk mitigation strategies. 9. Resource allocation and utilization analysis. Description: AI can analyze resource allocation across projects or departments, ensuring optimal use of resources. Graph, a pie chart or stacked bar chart showing resource distribution and utilization across different business functions. Insights, aids in ensuring that resources are aligned with strategic priorities and are not being wasted on low priority areas. 10. Employee performance and workforce analytics. Description: machine learning can provide insights into employee performance, retention risks, and workforce trends. Graph, a trend line or clustered bar chart showing productivity levels, retention rates, or workforce distribution over time. Insights, helps top management understand workforce dynamics, supporting decisions about hiring, training, and organizational structure. 11. Environmental and sustainability impact reporting. Description: AI can measure the environmental impact of production, including energy consumption, waste, and emissions. Graph, a line graph showing emissions or energy usage over time or a bar chart comparing sustainability targets versus actuals. Insights, provides insights into how the company is performing against sustainability goals, which is increasingly important for corporate responsibility and brand image. 12. Innovation and R&D performance tracking. Description: AI models can track progress in R&D, showing the rate of innovation, patent generation, or product development cycle times. Graph: a time series graph showing the number of new patents, innovations, or product launches per year. Insights: offers insights into the company's innovation trajectory, helping executives make strategic decisions about future R&D investments. How these reports and graphs aid decision-making for top management. Informed strategy setting: top management can use predictive insights to set realistic goals and make data-driven decisions about future strategy. Resource allocation: AI insights on resource utilization allow for more strategic allocation of resources, ensuring high-impact areas receive sufficient investment. Risk management: by identifying high-risk areas and potential disruptions early, executives can proactively develop mitigation strategies. Performance monitoring: continuous monitoring of production, financial, and quality metrics helps ensure the company stays on track to meet its goals. Sustainability and brand image: sustainability metrics help align corporate practices with environmental goals, improving brand perception and compliance. Each report and graph provides a strategic layer of insight, enabling top management to have a holistic view of company performance, risks, and opportunities, and supports effective decision-making in a highly competitive industry like semiconductors. Creating a Sankey diagram to represent the RDBMS schema and the semiconductor industry process flow could visually capture the relationships and flow values between entities. Based on the schema, the Sankey diagram would include 1. Nodes representing entities, example bank, government, manufacturing process, with flow values displayed as the size of each node. 2. Flows between nodes indicating relationships like information exchange, feedback, or material transfers, with flow values and types, example bidirectional or unidirectional, distinguished by different colors and flow line thicknesses. Here's how the diagram would be set up. Nodes: each unique entity from the entities table, example bank, government, process X, is represented by a node, with the node size proportionate to the flow value associated with each entity. Flows: connections between nodes will be directed and weighted according to the flows table, with attributes such as flow type, defines whether it's an information, feedback, or material flow, with color coding from the flow types table. Direction: unidirectional flows will have arrows pointing in one direction, while bidirectional flows, example feedback, will be represented by dual-headed arrows. The Sankey diagram provides a high-level overview of the relationships between various semiconductor industry entities, enabling top management to visualize the entire process and the resource or information flows. Suggested steps for building the Sankey diagram. 1. Map nodes based on the entities table data. 2. Define flows by connecting nodes as per the flows table and customizing based on flow attributes, type, direction. 3. Add color and thickness to flows, leveraging the flow types table for visual differentiation. This diagram would serve as a part of the decision support system, DSS, by visualizing complex interactions and aiding in the strategic analysis, such as identifying bottlenecks where flow values accumulate, indicating potential areas for process improvement. Highlighting flow imbalances that may signal inefficiencies or operational risks, useful for middle and operational management to monitor. Evaluating resource dependencies and understanding hierarchical relationships, particularly if entity relationships table data is included to show dependencies. Example in Python program. Risk analysis and mitigation strategies. Description: AI can assess risks across different areas like supply chain, market demand, and regulatory changes. Graph: a heat map showing risk levels across different factors or a risk impact/probability matrix. Insights: helps executives understand the most pressing risks and prioritize risk mitigation strategies. This Sankey diagram illustrates the process flow in the semiconductor industry, showing how different entities and stages are interconnected. Here's a detailed breakdown. Flow of information. 1. Bank, dark blue stream. Financial resources and investments start here. 2. Government, red stream. Additional support and regulation input from the government. Convergence point. Process X. Both the bank and government flows converge into the central process, indicating a crucial stage where financial and regulatory inputs are combined. Transition stages. 1. Supplier. After process X, the flow moves to the supplier, where raw materials or essential components are procured. 2. Manufacturing unit. The flow then moves from the supplier to the manufacturing unit, where the actual production of semiconductors takes place. Key takeaways. The diagram highlights the importance of both financial institutions and government support in the semiconductor industry's process flow. It visually represents how resources and inputs transition through different stages, leading to the final manufacturing of semiconductors. This visualization helps understand the intricate relationships and dependencies within the industry. Risk analysis and mitigation strategies heat map. Project documents. Title, project name. Risk analysis and mitigation strategies heat map. Axis details. Y-axis, risk factors. 1. Technology risk. 2. Supply chain. 3. Regulatory changes. 4. Market demand. 5. Financial risk. X-axis, impact levels. 1. Critical. 2. High. 3. Low. 4. Moderate. Color gradient. Purple represents lower risk scores. Yellow represents higher risk scores. Risk score scale ranges from 2 to 10. Risk scores. Each cell in the heat map indicates the risk score for a particular risk factor at a specific impact level. For example, technology risk at a critical level might have a high risk score, yellow. Supply chain at a low level might have a lower risk score, purple. Interpretation. The heat map helps visualize which risk factors pose the greatest threat at different impact levels, allowing for focused mitigation strategies. High risk areas, yellow cells, indicate where immediate attention is needed. How does that align with what you're looking for? Need more on any specific part? Explanation of the code. Data generation. We define some common risk factors, example supply chain, market demand, and impact levels, low, moderate, high, critical. Risk score values are randomly generated between 1 and 10 for simplicity, but you can replace this with actual risk scores from a data set. Data structuring. The data is organized into a data frame and pivoted to create a table suitable for a heat map. Each cell represents a risk score for a particular risk factor and impact level. Heat map creation. We use Go.heatmap in Plotly to create the heat map, with the color scale set to reds to visually represent higher risks with darker shades. The color bar provides a legend for interpreting the risk scores. Layout customization. Titles for the graph, X-axis, and Y-axis are set to make the plot informative and professional for executive review. Insights. The heat map visually highlights areas of concern. Darker red shades represent higher risks, helping executives quickly spot critical risks. This visualization enables top management to prioritize risk mitigation strategies by focusing on high-impact, high-probability risks. Explanation of code components. 1. Entity's definition. Each entity is defined with a name and flow value. 2. Flow's definition. Each flow specifies the source, target, flow type, and flow value. 3. Node and link settings. O nodes, represented by entities with their respective labels and a default color. O links, connections between entities based on flows with values and colors defined by flow type. 4. Plotting the diagram. Go.Sankey is used to create the diagram, with the layout styled and title added for clarity. This program will generate a Sankey diagram with labeled nodes and colored links, representing the different types of flows between entities in the semiconductor process flow. When organizing an AI/ML project, it's essential to define the project stages clearly and address each aspect systematically. Here's a suggested structure for the headings and content you could include in an AI/ML project report or proposal. This structure is designed to cover the core phases from initial planning to deployment and evaluation. 1. Project title. Example, predictive maintenance for manufacturing equipment using machine learning. 2. Executive summary. Brief overview of the project, objectives, and expected outcomes. Key takeaways and the potential impact of the project on the business or field. 3. Background and motivation. Explanation of the problem or opportunity. Insights into why this problem is relevant and what triggered the need for an AI/ML solution. Any previous work or solutions that highlight the gaps this project aims to address. 4. Project objectives. Clear, measurable goals of the AI/ML project. Define the key questions that the project seeks to answer. Expected deliverables, such as predictive models, a dashboard, or a deployed API. 5. Scope of the project. Define boundaries, and what will and will not be included in the project. Clarify any assumptions, limitations, or exclusions that are necessary for project completion. 6. Data collection and understanding. Data sources, identify and describe the data sources. Data exploration, summary of exploratory data analysis, EDA, including distribution, correlations, and any insights. Data cleaning and pre-processing, outline of the steps taken to clean and pre-process the data. Feature engineering, new features derived from existing data, and rationale for their inclusion. 7. Model development. Model selection, overview of the models being considered and the rationale for their selection. Training and validation, methodology for splitting data, cross-validation techniques, and performance measures. Hyperparameter tuning, describe methods used to optimize model parameters, such as grid search, random search, or Bayesian optimization. 8. Model evaluation and results. Performance metrics, key performance indicators such as accuracy, precision, recall, F1 score, AUC for classification, RMSE, MAE for regression, etc. Comparison of models, comparative analysis of various models used in terms of performance. Interpretability, model explainability and interpretability approaches, example feature importance, SHAP values, LIME. 9. Deployment strategy. Deployment environment, overview of the deployment environment, such as cloud platforms, edge devices, or on-premises servers. Model serving, details on model serving, example REST API, gRPC, framework, and technology used, example Docker, TensorFlow serving. Versioning, approach for model version control to manage updates and iterations. Monitoring and maintenance, monitoring strategies to track model performance post-deployment and address data drift or performance degradation. 10. Model maintenance and retraining. Data pipeline, description of automated or semi-automated data pipelines for continuous model improvement. Feedback loops, mechanism to collect real-world feedback and performance data. Retraining frequency, define schedule or conditions for model retraining to address changes in data distribution or business needs. 11. Risk analysis and mitigation. Data risks, risks related to data quality, availability, and privacy. Model risks, risks associated with model bias, overfitting, or underfitting. Operational risks, risks in deployment, such as infrastructure failure, latency issues, or scalability challenges. Mitigation strategies, outline of strategies to mitigate each identified risk. 12. Ethical considerations. Bias and fairness, measures taken to address any biases in data or model predictions. Transparency and accountability, description of how the model will maintain transparency and accountability. Privacy and data protection, steps to ensure compliance with data protection regulations, example GDPR, HIPAA. 13. Timeline and milestones. Project phases, high-level breakdown of the project phases, such as data collection, model development, testing, and deployment. Milestones, key milestones with expected completion dates. Gantt chart, visual representation of the timeline, if possible. 14. Budget and resources. Cost estimates, breakdown of costs for each phase, including data acquisition, model training, deployment, and maintenance. Resource allocation, detailed list of resources required, such as personnel, data scientists, ML engineers, hardware, and software. 15. Expected impact and success criteria. Impact, Potential benefits for the organization, users, or industry. Success metrics, metrics to determine if the project has met its objectives, example revenue growth, reduction in maintenance costs, improved accuracy. 16 Conclusion and next steps. Summary of key points and takeaways. Recommendations for further research, enhancements, or potential future phases. 17 References. Citations for any sources, research papers, frameworks, or technologies referenced in the project. Appendix, optional. Additional tables, charts, code snippets, or any other detailed information that supports the main sections. This structure provides a comprehensive approach to planning, executing, and documenting an AI/ML project. The specifics in each section should be tailored to the project's goals and technical requirements. Here's a breakdown of the image titled AI/ML project structure. Overview. Title, AI/ML project structure. Layout, flowchart design with a red curved line connecting two main components. Components. 1. Project title. Color, blue box. Position, on the left side. Description, represents the title of the AI/ML project. 2. Key sections. Shape, large rectangular area. Color, segmented into multiple horizontal colored sections. Content. Executive summary. High-level overview of the project's goals, objectives, and key results. Background and motivation. Provides context on why the project is being undertaken, including relevant history and the rationale behind it. Connection. A red curved line links the project title box to the larger rectangle, symbolizing the flow from the project title to detailed components of the AI/ML project. Purpose. This diagram visually outlines the essential components and structure of an AI/ML project, making it easier to understand how the project is organized and the flow between different sections. This layout gives a clear visualization of the critical parts of an AI/ML project and their interconnections, making it an excellent guide for project planning and execution. Thank you.